And we can recover the angular variation in both directions. So this new order parameter is, we think, unrelated to the all-in, all-out transition, but it already is there at room temperature. And obviously, by taking many, many measurements as a function of temperature, we can track the temperature dependence of this new parameter, eta. And here it is. So eta is, continues to be large, way above the Néel temperature, and it persists even above room temperature. So it's already an underlying symmetry breaking from C4 to C2, but its imprint on the all-in, all-out order is by distorting the D-wave pattern. Right? So that's our current understanding. This angular plot, torque versus angle, was performed, let's see. Oh, okay, so this is the part that we threw out, right? So this is the term that was linear in field, but you obviously can measure it, and you see that it actually is a very large effect. Even at 5 Kelvin, the torque, the magnetization at 180 degrees, I forget, I think this must be along y-axis, is significantly smaller than along x-axis. And it persists. Even at room temperature, we see a difference between the maximum. So this is yet another order parameter that onsets at 300 Kelvin. And it's always there, but it complicates a little bit the D-wave pattern that onsets below 120. So all these are puzzles that arise from the experiment, and they are very distinct from what you get in the conventional ferromagnet. Okay, that's all the stuff I have. In summary, we search for and observe an orthogonal magnetization that is distinct from this trivial Zeeman-induced transient magnetization. And it involves a spontaneous breaking of a Z2 symmetry. So this sketch summarizes the surprise, right? A field that's in plane generates perpendicular magnetization, but we can't tell if it's up or down, right? However, we can fix the choice by appropriate field cooling direction, but the effect on the whole pattern is very surprising. It's a D-wave pattern, and you can rotate it depending on whether you field cool along Y or along X, and we don't understand this. The domain wall is not conventional block motion. It gets frozen rapidly below 60 Kelvin with a gap of about 170 Kelvin. And well, what that means is the following. Let's say we field cool along a certain direction, and then we have the sample sit there at 4 Kelvin. And it doesn't matter what you do to the sample. You can run it to the highest field. This pattern is frozen in. So you cannot change it, I believe, even up to Tesla, although we haven't tested it yet. The only way you can change it is to warm it up above the transition and then field cool in the other direction. So the motion of the domain wall is very interesting to me. The experiment also uncovers a distinct order parameter, eta, that has nothing to do with AIAO, and that onsets at very high temperatures, and it has the effect of breaking the C4 to C2, right? Lattice symmetry. And it distorts the D-wave pattern, stretching it along the y-axis. Okay, this is all. Thank you for your attention.
What are the other alternatives for all in, all out states? Like, if it were not all in, all out, what else would happen?
Well, it could be 2 in, 2 out. Right? 2 in, 2 out, then that would bring in this spin ice problem with the possibility of monopoles or anti-monopoles. But I think the energetics do not favor 2V, 2R in this case.
Right, and when you say that when you freeze it below 60 Kelvin, it gets
No,
frozen.
the freezing is the domain wall motion.
So
Yeah, that's a separate question from the
is it then glassy
ground
or
state.
what is happening there?
No, we don't think there's anything glassy here. The appearance of magnetic hysteresis doesn't imply glassiness. Perhaps that's your, mixing up the two notions. When you see magnetic hysteresis, right, it doesn't imply glassiness. Luckily, the world's expert on the spin glass just walked out, so I can. So the spin glass is actually a very unusual state. It has nothing to do with magnetic hysteresis. Is that what you had in mind?
So what is the expectation for the behavior of free energy for the spin ice state? Is it just the usual ferromagnetic behavior? If you would have a spin ice state for 2 hours, would you expect just to see it just...
You mean the free energy for the spin ice state?
Yes, basically for magnetization.
I don't know. David stepped up. I don't know. You can write down free energy for the spin ice state.
I mean, so basically the cubic behavior is essentially the property of this all-in all-out state, right?
Right.
And what I really wanted to ask maybe about the pragmatic part is, can you be sure to actually see the all-in all-out state since, well, you expect it
So you have the existence of the paramagnetic. No. My point is that the argument that I presented at the very start was for the ideal AIAO state, right? So if you you could have an extraneous effect from the paramagnetic contribution, but it will not, because the cubic term now is so large, it will not completely suppress the cubic term. But symmetrizing the curves is a very powerful way to separate the two. Right? Because
that's what I was asking about the magnitude, basically.
it's very large. So if I hadn't anti-symmetrized the torque curve, you would just see the torque curve. You would just see the paramagnetic part overwhelm so you had to anti-symmetrize it.
Okay, if there's no further questions, let's thank Professor Ong again for his lecture. And